Hello, my name's Ivan Taylor, and I'm from Policy Dynamics in Canada's twin cities of Kitchener-Waterloo in Ontario. And today I'd like to give a presentation on some work that Keith Willett and I did on cybersecurity, modeling cybersecurity operations to improve resilience. And this was published as a book chapter in the Handbook of Security Science published by Springer. And it talked about resilience, which involves avoiding, withstanding, and recovering from an adversity. And in this case, the adversity is a cyber attack. And we're going to show how we can model a cybersecurity team that can adapt and recover the desired capability quickly. So I'm going to demonstrate how system dynamics modeling can be used to improve cybersecurity operations. System dynamics models behavior over time, which is particularly useful for studying resilience because we want to minimize the time the capability is degraded and restore the capability as quickly as possible. This shows the output or the final result from the model of the behavior over time of a capability or a system capability, which at time 0 is at 100%, and then at time 50 suffers a cyber attack that degrades the capability by 50%. And then we have two scenarios that we looked at, a balanced scenario in red and an adaptive scenario in blue. And we can see how the recovery occurs over time. Notice that the full recovery to 100% capability occurs at about time 144. However, at each point in time, the adaptive resource allocation strategy can get more capability up more quickly. And for example, if the required capability was less than 100%, say, for example, 75%, then the adaptive capability, adaptive resource allocation would return the system to the required capability much quicker than the balanced approach. So here are the phases of cybersecurity operations. It begins with the continuous monitoring of the system to evaluate when an attack occurs, and then there's a number of steps necessary um, to restore the system back to a certain level of capability, even if it's diminished capacity. And then with root cause analysis, we can recover the desired performance to the desired performance level. And finally, with lessons learned, can be fed back into the processes to avoid and withstand a similar attack in the future. This shows the system dynamics model in a diagrammatic form where each of the boxes represents a stock or a state of the system. And then each of the arrows with the valves shows the processes that move the system from one phase to the next. Notice up in the upper left-hand corner, we have an attack that occurs at a certain start time, has a certain intensity and a certain duration, and monitoring of the system determines when the attack is detected. And then, as we said, we go through a number of phases until we eventually restore the capability, possibly at a diminished capacity. And then with root cause analysis, we can get to a recovery of the full desired level of capacity. And from the root cause analysis, we get feedback that goes back into the monitoring and the other processes to possibly avoid and withstand future attacks of a similar nature. The important elements of this presentation that I want to discuss is that each of these phases requires time to execute and resources to execute. So I'm going to show how the resources can be allocated to reduce the time in each of these phases and thereby get the system restored and recovered as quickly as possible. So here's the resource allocation in a balanced system. So in this case, we have stovepipes or siloed resources. So each of the phases has a dedicated resources allocated to it, and you can see that the workflow is spread over quite a long timeline. Um, and, uh, and that leads to a slower recovery. And this shows the adaptive resource allocation, and it shows how the workflow can be compressed to the left and thereby recover more quickly. And in this case, the resources are not siloed. They are adaptive and in this case, people and technology can be applied more in a more adaptive way to recover more quickly. This graph shows the assignment of people, which is the primary resource in this workflow. And you can see that people, all the people are involved in monitoring at the beginning of the time. And then up until time 50, they're all involved in monitoring. And there's 9 people in this assumed cybersecurity team. And then at time 50, an attack occurs and the people scramble and start being allocated to various phases of the recovery processes. And eventually the system recovers from the attack and people gradually return to the monitoring function. So I hope this helps you understand what I am modeling in the balanced and adaptive allocation of resources and how these 2 different allocations affect the ability to recover from a cyber attack. So in summary, we built a system dynamics model of cybersecurity operations and demonstrated how 2 different resource allocation strategies would affect the system recovery from a cyber attack and improve system resilience. This is the citation to the book chapter that Keith Willett and I wrote. Keith is an expert in cybersecurity, and I was primarily involved in the modeling and simulation. It was published just last year in the Handbook of Security Science by Springer. And if you're interested in getting a copy of this chapter, you can contact me at ivan@policydynamics.ca. And if you have any questions or comments, you can also contact me and I'd be happy to discuss how this work could be used in your organization or any other modeling and simulation work you might wish to do in your organization. Thank you very much for your time and attention, and I hope to talk to you soon.